I would like to thank everybody for joining us today for the latest in our webinar series on targeted learning. Today, we are fortunate to have Dr. Laura Balzer with us here. Laura is an assistant professor of biostatistics and director of the causality lab at UMass Amherst. Her areas of expertise include causal inference and machine learning. These disciplines are integral to developing, evaluating, and implementing data-driven solutions in public health and medicine. Dr. Balzer is the primary statistician for 4 cluster randomized trials in East Africa. Her work is supported by the National Institutes of Health and has been recognized with the ASA's Causality in Statistics Education Award. And today, Laura is here to talk to us about the challenges and solutions in the analysis of cluster randomized trials. So Laura, thank you very much for joining us today, and we're all looking forward to hearing what you have to say. And now I will just turn it right over to you. Thank you.
Wonderful. Thanks so much for inviting me, Dr. Gruber, and thank you all for being here today. It's really an honor to share some of the work in the challenges and solutions in cluster randomized trials. So thank you so much for your attention, and I look forward to an interactive discussion and questions at the end. So this is a joint work with a lot of people, but in particular, I'd like to acknowledge my colleagues on the search team. So first, what are cluster randomized trials and why do we bother with them? So in cluster randomized trials, we randomize whole groups of participants, such as communities or clinics, to an intervention or comparator condition. Cluster randomized trials are commonly implemented when the intervention naturally occurs or is delivered at the cluster level. When we expect substantial dependence between participants within clusters or groups, or when we're aiming to learn the direct, indirect, and population level effects of interventions with proven or suspected individual level efficacy. There have been lots of exciting developments in CRTs. A recent review in cancer research found a 280-fold increase in their use from 1995 to 2014, but this review also found that only half of CRTs were analyzed correctly. And so today I want to address 2 challenges in the analysis of cluster randomized trials. The first is missing outcomes. While CRTs randomize clusters, they often measure outcomes on participants or individuals within those clusters. Another review found that over 90% of CRTs have missing outcomes for their participants. If there are shared drivers of outcomes and measurements, we know this can result in biased point estimates and misleading inference. The potential for bias is exacerbated when there are post-baseline drivers of measurement. As a concrete example, suppose that treatment increases engagement in care. And engagement in care further improves participant outcomes and their chances of being measured. This is illustrated in the simplified directed acyclic graph in the bottom right-hand corner. Now, this engagement in care is simultaneously a mediator of the treatment outcome relationship, as well as a confounder of the measurement outcome relationship. So this is the analogous to time-dependent confounding in the context of incomplete measurement. And in this scenario, standard analytic approaches for adjustment will fail. The second challenge faced by cluster randomized trials is there's often few randomized units. So most CRTs randomize a limited number of groups or clusters. A review found a median of only 30 units. This can result in chance imbalances on baseline determinants of the outcome. And adjusting for these imbalances and other covariates predicted of the outcome has been shown repeatedly to increase efficiency and statistical power. But the question becomes, how do I adjust optimally? We know the analysis plan must be a priori specified, but in CRTs, we're in this case where we may have many more potential adjustment variables than we do clusters. And therefore, it's unclear a priori which baseline covariates to include in a way that will maximize precision while controlling type 1 error. And our proposed solution to this is to a 2-stage targeted minimum loss-based estimator, or a 2-stage TMLE, with the goals of reducing bias due to missing outcomes and simultaneously improving efficiency when assessing the effect of the cluster level intervention. As indicated by the name, this is going to be a two-step process. Well, in the first stage, we focus on each cluster separately. And within that cluster, we're going to estimate a cluster-specific endpoint. And this will allow us to adjust for possibly differential measurements, missingness, or censoring at the participant level. Then in stage 2, we use those cluster-specific endpoints to estimate and obtain inference for the intervention effect now at the cluster level. And in stage 2, this provides an opportunity to adaptively adjust for cluster level covariates with the goal of increasing precision and thereby statistical power. As a motivating example, we're going to consider the search study. The search study approached HIV elimination through a broad community health framework. The intervention can be characterized as universal HIV test and treat, which is a program to go out and test entire communities for HIV. And for persons who are diagnosed or living with HIV, get them into care and on treatment as soon as possible and keep them in care and on treatment. This not only protects and promotes the health of the person living with HIV, but also can prevent onward transmission from in a serodiscordant partnership, so someone living with HIV to their negative partner, or from an HIV positive mother to her child. In the search study, we implemented universal test and treat through a community-based, multi-disease, and streamlined care approach. In the big picture here, our design was a pair-matched cluster randomized trial of 32 communities in rural Uganda and Kenya. Specifically, we had 10 communities in Uganda West, 10 communities in Uganda East, and 12 communities in the Lake Victoria region of Kenya. In more detail, search was a two-arm trial. Our intervention package consisted of multi-disease testing delivered through health fairs at baseline and annually in the intervention. The pictures on the right-hand side give you a sense of these health fairs. The top is in a rural farming village in Uganda, and the bottom is a fishing village in Kenya. These health fairs were 2-week out-of-facility events where we tried to get entire communities to come out and participate in their health. And we offered screening and linkage to care for things like hypertension, diabetes, malaria, as well as HIV. Additionally, for community members that did not come to the health fairs, we offered follow-up at a location of their choice, which was usually their home. In terms of treatment for these conditions, we offered universal eligibility, which means that as soon as you are diagnosed positive, you are eligible to get on treatment to manage those conditions. This is a contrast with some of the other guidelines for starting treatment, especially for HIV, that says, essentially, you have to be sick enough before you start treatment. And in terms of care for our participants, we offered a patient-centered, streamlined care approach with things like having a warm, welcoming environment, flexible clinic hours, and the big picture of treating the person as opposed to the disease. We contrasted this with an active control. So in our active control arm, we offered testing through the same health fairs at baseline, treatment according to Ministry of Health country guidelines, which rapidly changed over time to essentially be treat all or universal eligibility within 1 year of the trial start. And our care was the country standard. And so jumping to the big picture finding here. So we found that this community health approach with a patient-centered and multi-disease model rapidly increased population level HIV viral suppression, which is the proportion of all HIV positive persons who are suppressing viral replication, from a baseline of 42% to 79% in the intervention arm, as compared to 68% in the active control arm. We also saw dramatic reductions in HIV incidence within arm and improvements of community health, reductions of 21% in HIV-related mortality, 59% of HIV-related tuberculosis annual incidence, and improvements in hypertension control. Now, with this search story in mind and those previous two challenges of missing participant outcomes and few randomized units, I want to dive into how we got these numbers and the really statistics underlying this in the rest of the talk. So the outline today, again, we're going to be focusing on this novel method of two-stage TMLE. In stage one, we're going to use individual level TMLE to adjust for incomplete outcome ascertainment within each cluster or community separately. And again, here, our goal here is to reduce bias due to missing individual level outcomes. Then in stage two, we're going to use a cluster level TMLE to data adaptively adjust for baseline covariates when estimating the intervention effect. And our goal here is to improve precision and thereby statistical power. So a key endpoint in search is known as the UNAIDS 90-90-90 target. This target specifies that 73% of all people living with HIV should be suppressing viral replication. And importantly, this all people living with HIV means that it's regardless of their care status. So this is often called population level HIV viral suppression. This is seemingly a simple conditional probability. So it's the conditional probability of suppressing viral replication given you're HIV positive, which we can, of course, rewrite in terms of the joint probability of being HIV positive and suppressing viral replication divided by the prevalence of HIV. While it's easy to write down, it's nonetheless challenging to identify and estimate population level viral suppression. First, the number of persons with HIV in the population is generally unknown. And those who test for HIV may not be representative of those who do not. And therefore, there's a potential for bias in our estimates if testing is related to HIV status. Sorry, dog break. Consider, for example, health-seeking behavior. Suppose individuals with higher health-seeking behavior are more likely to test for HIV, but also less likely to be HIV positive. If we sought to estimate population level prevalence of HIV with the raw proportion among those who tested, that would actually underestimate the true prevalence of HIV in the population of interest. Similar challenges apply to measurement of plasma HIV RNA levels or viral loads, in that it's often incomplete. And again, there could be a potential for bias if measurement is related to underlying viral suppression status. This could occur concretely if HIV positive persons not on treatment are also less likely to have their viral load measured. And so what's the challenge we're getting at here? The challenge is really missing data. And when I think about challenges and think about being an expert in causal inference, I like to pretend I'm this little happy-go-lucky wizard here who can do any intervention they want. And so what do I want? I want these true population level metrics. And how would I get there? Ideally, I'd go out and obtain an HIV test on anyone not already diagnosed. So those are previously HIV negative persons or HIV unknown persons. And then I conduct a second intervention, which is actually dynamic or personalized intervention, to go out and get a viral load in all persons living with HIV. What do we have in reality? In reality, we have incomplete data with possibly differential ascertainment. And in many scenarios, the missing completely at random, or MCAR, assumption is not likely to hold. Even in large CRTs with high measurement coverage, those who are measured may not be representative of those who are missed. And so a solution we pose to this is the two-stage TMLE, where we're going to separate out control for differential measurement from evaluation of the intervention effect. Again, in stage one, which I'm going to focus on for the first part of the talk, within each cluster separately, we're going to identify and estimate a cluster-specific endpoint corresponding to a hypothetical intervention to ensure complete measurement of individual level outcomes. And by fully stratifying on cluster, this actually allows the missingness or measurement mechanism to vary by cluster. Then in stage two, we're going to use those cluster-specific endpoint estimates to evaluate the intervention effect. But again, focusing on stage one, for identification asks us what assumptions are needed to move from a wished-for causal parameter, corresponding in this case to hypothetical interventions to prevent missing data, to a statistical parameter or statistical estimand. And we can only make this translation under clearly stated and painfully evaluated assumptions. And in doing so, we can use statistical adjustment to quote unquote level the playing field. And this is done, for example, by assuming that within values of adjustment covariates, persons with measured outcomes are representative of persons with missing outcomes. As a concrete example, if we could think about identification assumptions that we use in search for population level viral suppression, we can again split this into the numerator and the denominator. So the denominator of HIV prevalence, we are willing to assume that for persons without a prior HIV diagnosis, within values of baseline covariates and testing history, HIV prevalence among those tested was representative of prevalence among those missed. And for the numerator of being as the proportion who are HIV positive and suppressing viral application, we are willing to assume that for HIV positive persons who have started treatment, within values of baseline covariates and care history, so this is the whole past history of testing, ART use, and past suppression, current viral suppression among those with a viral load measured was representative of viral suppression among those with a missing viral load. And from these, we can define the corresponding statistical estimands or parameters. But going back to a bigger picture of what do we do once we get those statistical parameters, so a more general story. So given those statistical parameters within each cluster separately, we could estimate them with a non-parametric stratification-based approach, where, for example, within each level of the adjustment variables, we simply count up the number with the outcome and divide by the number measured. And then we average those strata-specific estimates. This approach is nice, it's simple, it's intuitive, but unfortunately, it quickly breaks down due to empty or sparse cells. So suppose, for example, that we thought age, deciles were the only drivers of measurement and health outcomes, then we'd have 1,000 strata in which we wanted to count up the number measured and divide, or count up the number with the outcome and divide by the number measured. In the search example, there's many variables that can potentially impact measurement, HIV status, and viral suppression. Some time-fixed examples are relatively time-fixed, include age, sex, occupation, and education. But then we have time-varying factors, and these time-varying factors could be potentially impacted by the intervention, including the history of testing, care, treatment, and viral suppression. So an alternative to a non-parametric approach is a completely parametric approach. Two approaches commonly relying on parametric assumptions include parametric G computation, sometimes called parametric G formula, and inverse probability weighting. In parametric G computation, we could, for example, assume that a main term's logistic regression accurately characterize the probability of viral suppression given the adjustment factors. Alternatively, in inverse weighting, we could assume that a main term's logistic regression accurately characterize the probability of being measured or tested given those adjustment factors. In both cases, if we misspecify those parametric regressions, we could be at risk of biased point estimates and misleading inference. And in this case, increasing our sample size does not help. It just gives us more precision around the wrong answer. So if you guys remember Brainy Smurf, he's this little blue dude that runs around town pretending to know more than he actually does. And I think sometimes we rely on these parametric regressions. We pretend to know more about the data generating process than we actually do. And here's where supervised machine learning can come to the rescue. And it can allow us to estimate complex relationships in the data flexibly, and thereby avoid introducing new unsubstantiated assumptions during the estimation stage. But with all things, it comes with challenges. And in this case, there's a lot of really new, exciting developments in supervised machine learning. Seems like coming online every day. And it's often unclear which is the best for the problem at hand. And so potential solutions to this is Superlearner. Superlearner uses cross-validation or sample splitting to build the best weighted combination of predictions from a whole set of candidate algorithms. In other words, superlearner is an ensemble or stacking method that combines together predictions from things like parametric regressions, penalized regression, neural net, adaptive splines, and so forth. Briefly, we can obtain this weighted combination by regressing the observed outcomes on cross-validated predictions from each of the candidate algorithms. And this is a special regression in that what we're minimizing corresponds to the loss function of interest, and we constrain the coefficients to be non-negative and sum to 1. But the big picture is those coefficients then become the weights, and we can apply those weights to get the best combination of predictions from a whole set of candidate algorithms. In other words, instead of just betting on one prediction algorithm, we allow the best team to win. So if you know Captain Planet always said, by our powers combined, we can stop air pollution and save the environment. Superlearner, at least in my mind, says by all of our algorithms combined, we can come up with an even better prediction function. What's the challenge here? The challenge is that prediction, in this case, is not the same thing as causal inference. So you might be wondering, why shouldn't I just use superlearner in the place of those parametric regressions in G computation or inverse weighting? The goal of the supervised machine learning task here is prediction. And that's fundamentally a different goal than causal effect estimation. And briefly, that means we have the wrong bias variance trade-off. And additionally, there's no reliable way to obtain statistical inference when we're plugging in superlearner or other machine learning based predictions or estimates into a single robust estimator, such as G computation or inverse weighting. Thankfully, over the last 15 years or so, there has been lots of solutions posed to this problem. One such solution is the general field of targeted learning, and in particular, targeted minimum loss-based estimation, or TMLE, which is a general framework for constructing double robust, semi-parametric efficient substitution estimators. Without getting into all the details today, TMLE updates or target those initial predictions from machine learning to focus estimation to where it matters most for the question at hand, and get us back accurate quantification of uncertainty, thereby integrating machine learning or data adaptive estimation with formal statistical theory. And so for me, TMLE is our Robin Hood here, where we're targeting to hit the bullseye to get us the best bias variance trade-off for our research question of interest, as well as get us back 95% confidence intervals that we know and love. Without getting into the technical details, here's just a brief overview of how one could implement TMLE when dealing with missing data on the outcome. So first, we would subset the data to those who are measured, so participants that have a known outcome. Then we would use superlearner to flexibly model the relationship between that outcome and the adjustment factors. We then use the output from superlearner to predict for all observations their outcome. So that includes participants with known as well as unknown outcomes. And step 3 is that special targeting or updating step, where we target those machine learning based predictions using information in the propensity score, which is here the probability of measurement given the adjustment set, which we can also fit with superlearner. And finally, we average those targeted predictions. And so now let's all apply this to the search study. And in this case, we're focusing on estimating population level HIV viral suppression. So here's the proportion of all adults living with HIV who are suppressing viral replication below 500 copies per ml in Uganda and Kenyan communities. And we're going to estimate population level viral suppression within each cluster separately, and then aggregate it up to obtain arm-specific estimates. For now, I'm going to be focusing only on the intervention arm. And in doing so, have cross-sectional snapshots among residents or adults here over successive years of the intervention, including those who move in or age in, but exclude those who die or move out of the study communities. So in search, we achieved high levels of testing through the multi-disease health fairs with follow-up for non-participants. For example, at baseline, 90% of over 150,000 adults tested for HIV. And we use the same mechanism to measure viral loads. Given this population-based ascertainment of HIV status and viral load status, as well as the high measurement coverage, it could be tempting to estimate population-level suppression with the raw proportion. So just count up the number that have a suppressed viral load and divide by the number who have their viral load measured. This, however, would be relying on a stronger assumption on missing data, specifically the missing completely at random assumption. Nonetheless, let's see what happens when we do this. So here are our results. On the y-axis, we have our estimates of population level viral suppression in the intervention arm. This is in percent. And then on the x-axis, we have the study timeline from baseline to the end of study with 3 years of follow-up. This dashed line here, horizontal line, is the UNAIDS 90-90-90 target for 73% suppression. And the black vertical lines are the 95% confidence intervals respecting the cluster as the independent unit. And so this unadjusted approach of just taking the raw proportion among those measured suggested that half of all adults living with HIV were suppressing viral replication in our rural Ugandan and Kenyan communities. And within 1 year of the search intervention, this jumped 30 percentage points to 80%, and vastly surpassing the UNAIDS target of 73% ahead of schedule. And this further jumped to 85% within 2 years of the intervention. But again, recall that this approach is really relying on that strong missing completely at random assumption. So now let's see what happens when we do some adjustment for a few baseline characteristics. And so now in medium blue, these are the results when we are adjusting for sex and age group, as well as community. So we're fully stratifying on those variables, and this would be equivalent to fitting a saturated regression in G computation or inverse probability weighting. And we see here that relaxing that missing completely at random assumption to allow missingness to depend on a few baseline characteristics yields slightly lower, but not meaningfully different estimates. So at baseline from 50% to 49%, year 1 from 80 to 79, year 2, 85 to 84, and so forth. But now let's see what happens when we further relax those missing data assumptions to allow measurements to depend on both baseline and post-baseline variables. So in dark blue, we now have the fully adjusted approach, which is again controlling for baseline and time varying predictors using TMLE with superlearner. And so at baseline, our estimates drop from 50% to 42%, at year 1 from 80% to 71%, year 2, 85 to 76, and so forth. And so across the board, we see that this fully adjusted approach yields substantially and meaningfully lower estimates. And for those of you who do not work in the field of HIV prevention and treatment, I again want to stress that these are meaningfully lower estimates that could impact participant outcomes, as well as the allocation of limited resources. Bringing it back to the more statistical side of things, I want to issue caution when relying on the missing completely random assumption or only baseline adjustments when estimating the cluster-specific endpoints or arm-specific endpoints in randomized trials. But bringing this back to our two-stage TMLE, here are results comparing our intervention arm, again shown in blue, to the control arm shown in red. These are fully adjusted estimates. So at the end of the study, year 3, we found that population level HIV viral suppression was 11 percentage points higher in the intervention versus control, which brings us to our next question of what is the effect of the search intervention as compared to the active control. And so this brings us to the second part of the talk. In the first part of the talk, we've used an individual level TMLE to adjust for incomplete outcome ascertainment within each cluster separately. Now in stage 2, we're going to use a cluster level TMLE to data adaptively adjust for baseline covariates when estimating the intervention effect. And again, here's a big picture of our two-stage TMLE to make sure we're all on the same page. Again, stage 1, we stratify fully on cluster and estimate the outcome. This provides an opportunity to adjust for differential measurement or censoring at the individual level, as we demonstrated previously for population level HIV viral suppression. Now in stage 2, we're going to estimate the intervention effect. In stage 2, our observed data are at the cluster level, and we can summarize them as follows. W are our baseline cluster level covariates. A is the indicator of being randomized to the intervention arm, and Y is our outcome. And this outcome is estimated for each cluster during stage 1. And so let's talk about stage 2 effect estimations. So at the cluster level, there is no confounding, and we have complete follow-up. So a simple and intuitive way to estimate the intervention effect is to implement an unadjusted estimator, which you can do by contrasting the average outcomes between treatment arms. So we can take the average outcome among intervention communities and subtract off the average outcome among control communities, or do this on the relative scale. Assuming that our stage 1 approach appropriately accounts for missingness on individual level outcomes, this approach will be unbiased. It's simple, it's easy to do, it's easy to explain, but unfortunately it's often inefficient. As we previously discussed, adjustment for baseline covariates in randomized trials can increase precision. In the case of trials with few randomized units, such as cluster randomized trials, this can help us control for some chance imbalances on pre-intervention determinants of the outcomes between arms. We can also adjust for measured baseline covariates that were unavailable during matching, if matching was conducted. So for example, SEARCH was a pair match trial where we randomized the intervention within match pairs of communities. But when we did that pair matching, we did not have a good measure of baseline HIV prevalence, which is a known driver of the primary outcome, which was HIV incidence. Altogether, it's been shown repeatedly for many years that adjustment for covariates predictive of the outcome can increase study power without bias, even in small trials. And so one potential to do this, so how would you actually estimate the intervention effect in stage 2 using some adjustment, would again be with TMLE, and it'd be implemented as follows. First, we'd regress our outcome on the intervention assignment A and the adjustment variables W. For example, we can use logistic regression of the estimated viral suppression on the intervention assignment and baseline prevalence and region. Then we use the coefficients from this first regression to predict the outcome for all clusters under the intervention and under the control. We then target or update these predictions using information in the known or estimated treatment mechanism. So we know with probability 1/2, a given cluster or community is either intervention or control. But again, we can estimate this treatment mechanism to provide a second opportunity to adjust for predictive covariates. And finally, we could average those targeted predictions and contrast on whatever scale of interest. But the stage 2 challenge here is, which covariates should I include? We know their analysis plan must be a priori specified, or must be pre-specified, but it's often unclear from the get-go which covariates we should be including in the adjustment set when predicting the outcome or when estimating the known treatment mechanism. Furthermore, the size of the adjustment set and the aggressiveness of our adjustment is often restricted by the number of independent units. Recall in the SEARCH study, we have 32 communities, 16 matched pairs, and many more potential adjustment variables, including things like region, baseline HIV prevalence, baseline viral suppression, and so forth. And so our solution here is to apply adaptive pre-specification in stage 2. Adaptive pre-specification is a modification to the previously described TMLE to data adaptively select the candidate TMLE that maximizes precision. This builds on the principle of empirical efficiency maximization. We further incorporate collaborative estimation of the known treatment mechanism for further gains in precision. Again, we know with probability 1/2, a cluster is intervention or control. And so in this case, we're only going to estimate the treatment mechanism If it further improves efficiency and precision, otherwise we'll treat it as known. How does this work? First, we need to pre-specify a bunch of things. We're going to pre-specify candidate estimators of the outcome regression. So for example, we can pre-specify a set of working regression models that have an intercept, main terms for the treatment, and one additional baseline cluster level covariate. We can additionally pre-specify candidate estimators of the known treatment mechanism, and can again consider working regression models with an intercept and a main term for one baseline cluster level covariate. Each one of these candidate estimators of the treatment mechanism would yield a different update to our initial estimator of the outcome regression. We also need to pre-specify a measure of performance. In this case, our loss function is going to be the squared influence curve for the TMLE. Thereby, the expectation of that loss function or the risk is the variance of the TMLE. We also need to pre-specify a cross-validation scheme to select the candidate estimator. And here we're going to use V-fold cross-validation to select the candidate TMLE that has the lowest cross-validated risk estimate. In other words, the smallest cross-validated variance estimate. In small trials, such as cluster randomized trials, we recommend doing this with leave one out or leave one pair out cross-validation. With all of these ingredients, we now have a fully pre-specified procedure to data adaptively select the adjustment variables, and thus the TMLE, which maximizes the empirical efficiency. And just a quick note on statistical inference of these procedures. Under the following conditions, we have that two-stage TMLE will be an asymptotically linear estimator, meaning the estimator minus the target of inference can be written in first order as an empirical mean of an influence curve or influence function. Importantly, this influence curve or influence function is at the cluster level. And this remainder term Rn is going to 0 in probability. The conditions include the usual regularity conditions on the stage 2 estimators. And these are guaranteed to hold when we're using adaptive pre-specification to choose among classes of generalized linear models. But here we need a second condition, this two-stage estimator, is that estimation of our cluster level endpoint, y, in stage 1 provides a negligible contribution to the remainder term. Just in a bit more detail, for this to be negligible, we need that our stage 1 estimators of the expected outcome and missingness mechanism to be in a Donsker class and to converge to their targets at fast enough rates. We also need some conditions on the within cluster dependence and the cluster size relative to the total number of clusters. But I really want to highlight condition 2A here, which emphasizes that for two-stage TMLE to work, we need a consistent estimator of the cluster level endpoint. In other words, missingness matters. It's also worth noting that these conditions apply to all two-stage estimators, such as running a t-test on the cluster means. All right, so we've gone through the 2 stages of our estimator here. And before showing how this all applies to the search study, I want to show a quick simulation study. So in the simulation study, we have 30 clusters. In each cluster, the number of participants is randomly sampled from 100, 150, or 200 participants. In this case, we randomize the cluster level intervention within matched pairs of clusters. And in these simulations, I have an individual level mediator or a post-baseline covariate, as well as differential outcome ascertainment by arm. So here's a simplified directed acyclic graph to summarize the simulation setup. And as shown here, again, we have this individual level mediator. So it mediates the treatment outcome relationship, but simultaneously confounds the measurement outcome relationship. Additionally, we have differential measurement here by arm, but also influenced by that mediator and baseline covariates. In the simulation study, I'm going to be comparing the following estimators. So a student t-test, so it's the only unadjusted estimator under consideration. The covariate adjusted residuals estimator, or CARE, of Hayes and Moulton. Mixed effects models, sometimes called random effects models. Generalized estimating equations, or GEE. double robust GEE or DRGEE, which is an extension of GEE to incorporate weights to adjust for missingness, and then the two-stage TMLE proposed here. I'm going to focus on assessing the risk difference and the risk ratio when we either break or keep the match pairs that were used for intervention randomization. And so first, focusing on results for the risk difference. In the simulation study, the true value of the risk difference was negative 9.2%. And three estimators that go after the risk difference include the student's t-test, covariate adjusted residuals, and this two-stage TMLE. For all three estimators, I've shown results when we break the matches, so we ignore the pair matching scheme in the analysis, or when we keep the pair matching scheme in the analysis. For each, I have the point estimate, or the average point estimate in percent, the bias on the absolute scale, or the additive scale, also in percent, the standard deviation of the point estimates, the average standard error estimate, the 95% confidence interval coverage, so the proportion of times the 95% confidence intervals contain the true value, and statistical power, or attained statistical power, in the proportion of trials that correctly reject the false null. So first, looking at the t-test, we see, as expected, it's not adjusting at all for missing data. So assuming the missing completely at random assumption, which does not hold, it's extremely biased, overestimating the intervention effect by nearly 23%, and attaining confidence interval coverage less than 1% in both settings. Covariate adjusted residuals is less biased, so about 8.5% overestimating the effect when breaking the match and 6.2% when keeping the match. But this bias is substantial enough to prevent accurate inference. So confidence interval coverage, much less than nominal rate of 95%. The two-stage TMLE, on the other hand, exhibits minimal bias and very good confidence interval coverage. Also expected by theory, we get more power when keeping versus breaking the matches here. So from 50% to 55%. Now focusing on the risk ratio. So in this simulation study, the true value of the risk ratio was 0.88, so a 12% relative reduction. And again, we have a very similar setup here. Left-hand side is when we break the matches, right-hand side is when we keep the matches. Comparing mixed models, GEE, DRGEE, and our two-stage TMLE. So in our mixed models case, we now see the bias here, which is now on the relative scale. So in this case, we tend to overestimate by about 10% the intervention effect, both when breaking and keeping the matches. And this bias is substantial to prevent accurate inference. We see about 58% confidence interval coverage in both settings. GEE exhibits similar magnitude of bias, but much lower confidence interval coverage of 18.6% and 5%. And DRGEE exhibits the most bias and has 0% confidence interval coverage. In contrast, our two-stage TMLE is essentially unbiased and has good confidence interval coverage under both settings. And again, we see a bit more power when keeping versus breaking the matches in the analysis. And now bringing this all back to the search study where we started, here's our summary, our big picture, one PowerPoint slide of what we learned. And now what I want to do is for a few select endpoints here, really dive into how using adaptive pre-specification in stage 2 can improve statistical precision. So I'll be focusing on 3 outcomes. First, the 3-year cumulative incidence of HIV, which was the primary study outcome. Second, the incidence of HIV-associated tuberculosis or death due to illness. And finally, population-level HIV viral suppression, which we know, which I've covered several times so far. And again, I want to be focusing on efficiency gains when we're using TMLE with adaptive pre-specification in stage 2, after in all cases, we've already adjusted for individual level missingness in stage 1. So I'm going to be comparing TMLE with adaptive pre-specification to an unadjusted approach in stage 2, and this unadjusted approach both when we break or keep the match pairs that were used for intervention randomization. And so here are results, again, focusing on stage 2. So all of these are already adjusting for missing data in stage 1. Our 3 endpoints: HIV incidence of HIV-associated TB or death, and population level viral suppression. For each, I have the point estimate, the 95% confidence interval, and the relative efficiency. This is defined as the precision gain or relative variance reduction over the unadjusted estimator when breaking the matches. So first, focusing on the primary endpoint of cumulative HIV incidence, we see across the board that we get pretty much the same point estimates. But as predicted by theory, we get more efficiency from keeping the matches. So using an unadjusted stage 2 estimator, but keeping versus the breaking the matches would be about 3.1 times more efficient. And using the primary approach in search, which was the TMLE with adaptive pre-specification, and keeping the matches in stage 2 was 4.6 times more efficient. A similar picture is shown for the incidence of HIV-associated TB or death. We see, again, very similar point estimates, but an unadjusted stage 2 approach keeping the match was 2.2 times more efficient than an unadjusted stage 2 approach breaking the match. Furthermore, using TMLE with adaptive pre-specification was 2.6 times more efficient. For population level viral suppression, we actually see a different picture. In this case, we have the exact same point estimates and the exact same inference. And this is because our pair matching scheme was with respect to the primary outcome of HIV incidence and didn't really help us to gain efficiency for the secondary outcome of population level viral suppression. Additionally, we don't get a gain from using TMLE with adaptive pre-specification because none of the pre-specified adjustment variables improve precision over the unadjusted approach. And so TMLE with adaptive pre-specification will actually reduce or default to the unadjusted estimator in that scenario. And with that, I want to wrap up so we have some time for questions. So here we proposed and evaluated a novel 2-stage TMLE to simultaneously address bias due to missing individual level outcomes and try to improve precision when estimating the effect via few randomized units. This 2-stage TMLE is applicable to a wide range of measurement schemes, so single cross-sectional sample, repeated cross-sectional sampling, or longitudinal follow-up. Also applicable to various endpoint types, so we can have a binary endpoint, continuous time to event outcomes, as well as causal parameters. Our simulations demonstrated the potential of 2-stage TMLE to overcome some of the shortcomings of existing methods, especially when there is post-baseline drivers of measurement. And our application to the search study demonstrated some real-life improvements. But of course, there are limitations in areas of future work. So a limitation here is that our stage 1 adjustment for missingness occurs within each cluster separately. And by fully stratifying on cluster, that can limit the breadth of adjustment when the cluster-specific outcome is rare or when the cluster-specific sample size is small. Additionally, our stage 2 adjustment for precision gains was at the cluster level only. This doesn't allow us to adjust for individual level covariates, again, for the purposes of improving precision. And we're hoping to work on these limitations in our future work. And so with that, I'd like to thank you so much for your attention. Thank you, Dr. Gruber, for organizing and inviting me. Thank NIH and PEPFAR for supporting search. We're grateful for all work on search, our multilateral partners, and the communities we serve. And very briefly, just acknowledge some of my colleagues from around the world who work on the search team. With that, I will turn it over to you, Susan, for questions. Thank you.
Thank you, Laura, for that tour through cluster randomized trials for HIV. It was very interesting. I want to say to the audience that in past webinars in the series, we've talked about TMLE itself being a 2-stage estimator, and in the first stage you estimate the outcome regression and the propensity score, or the G portion of likelihood, and the second stage you target. And that's a different use of the two-stage, the phrase two-stage than what we've heard today. And I think that you all probably figured that out for yourselves. But I just wanted to point that out that you know, in what Laura presented, there's a TMLE happening in stage one. That's a two-stage procedure, and a TMLE happening in stage two. That's a two-stage procedure. So I want to invite you to enter questions in either the chat window or there's a Q&A at the bottom of your screen. And I'll be monitoring that, and I'll read those to Laura when they show up. And in the meantime, while you're typing your questions, I'll ask a question. This is actually just a little detail, Laura. On slide 17, when you were talking about estimating the prevalence of HIV, this is in stage one, when you're trying to do the cluster specific adjustment for missing outcomes. It says here for the denominator, the HIV prevalence, within values of baseline covariates, testing history, HIV prevalence, among those testing was representative. Okay, so my question was, if you have a strata who have not been tested, then you don't know that you have a complete positivity violation. What am I missing something?
No, not at all. I mean, this is still quite a strong assumption, and it still does rely on positivity. And so if we have a strata of persons with certain baseline characteristics that never got tested, then we have no information about what HIV prevalence is among that strata. Through the out of facility, I have it somewhere here. Through this approach of out of facility testing, we actually saw quite high coverage. As I said, 90% of all adults living in the communities tested for HIV at baseline. And the other key thing that I should have mentioned is the reason that we know that it's 90% is because right before we did the search study, we conducted a rapid census. And so in that rapid census, we gathered a lot of information about baseline covariates, but also learned who was in our study communities. So therefore, we knew who was missing. Does that answer your question?
Yes, it does. Thank you.
I can also show all these bonus slides. If it's helpful, here's like the actual identifiability result. I just didn't go over it in detail. But for sure, there's a positivity assumption in here that you have to have a positive probability of being tested, given that you were previously HIV unknown or negative within all values of past testing history and baseline covariates.
Okay, thank you.
Sure.
I don't see any other questions. So I think that what we'll do is we'll wrap it up. And I just want to thank you once again for giving us this talk about how you can apply TMLE when there's, at the cluster level, only 32 communities, 16 pairs, and still get some effective data adaptive learning and targeting.
Yeah, that's been a huge amount of my work, is how do we take these asymptotic results and apply them in a setting where we have highly dependent outcomes and very few truly independent units, or truly under the assumption that our clusters are independent units.
Mm-hmm. Yeah. So thank you. We'll keep paying attention to the papers. And I want to mention that some of the work here is very shortly going to be posted on arXiv, and you'll be able to look at the papers. And when that happens, we'll make sure that the URLs for the papers are available either on YouTube or on the Putnam Data Sciences website, or you can just search, obviously, arXiv for Dr. Balzer's name. Okay, thank you very much, everybody, for attending. And thank you, Laura, again, for speaking with us today.
Thank you so much for having me. Really appreciate it.